Hello everyone, and welcome back. During the last couple of lectures, we have been looking at motion in one dimension. We started out by determining a way where we could describe the position of an object, x of t, perhaps in general as a function of time, and then we defined some quantities, we figured out how to then relate that to the velocity of the object and then the acceleration of the object by differentiation, differentiating x one time to get velocity, a second time to get acceleration. And we could certainly imagine we could go back the other way. If we had the acceleration, we could figure out the velocity and then the position as a function of time by anti-differentiation or integration. So we have these relationships through differentiation, and then what we did was we limited ourselves to a particular kind of motion, uniformly accelerated motion, and we derived the four kinematic equations, and then last time in particular we looked at some examples of that. What we're going to do now is extend these ideas to 2 and even possibly 3 dimensions, which brings us to section 3, vectors and motion in 2 and 3 dimensions. Remember what we did for one dimension. The first thing we had to do was we defined a coordinate system. And in particular, we called it the x-coordinate. So we've got this coordinate system, a single axis, one line. We define an origin, and then we define one side in general to the right as having positive values and to the left as having negative values. And this was really all we needed to do in order to define enough information to describe the motion. We just had to have one coordinate system. Well, what are we going to do for 2-dimensional motion, and even 3? We'll look at 2-dimensional motion basically, and 3 dimensions is just will be a very straightforward extension of 2 dimensions. Well, you might say, okay, well, all we need to do is just add another dimension, and really that is all we do. We add another dimension. If we define this one as x, we could call this one as y. Likewise, define one direction as positive, typically upward as positive, downward as negative. Those definitions are purely arbitrary, but it will turn out later on that it will be helpful if we keep this particular orientation. We might rotate these or something, but having the relative positions of the positive sides and the negative sides will help later on. We'll see that later, but we don't need to worry about it. So we might think, okay, all we need to do is just define these 2 coordinates, and that certainly is true. We can define the motions in 2 dimensions using just x and y's, but there's actually a quantity or a type of quantity that's going to be very, very helpful for us in this description of motion, and it will be very, very helpful later on when we start looking at some more complicated things. And that kind of a quantity is what we call a vector. When we have certain numbers, or certain quantities, which can be completely described by a number and typically a unit, those kinds of quantities are what we call scalars. For example, the mass of an object. What is the mass of this cup? We can describe that with a single number, maybe 1.125 kilograms or something like that. That's all we need to do to describe the mass of an object. It's a single number. That's what we call a scalar. Scalars just think of as having a size, the size of the value, or in general, a magnitude. Now, I want to be a little bit careful because typically we'll use magnitudes in a specific way for vectors, but scalars can be negative. Scalars can be negative or positive. If we think about temperature, temperature would be another example of a scalar. We can have negative temperatures, and that just means temperatures that are below 0. Positive being above 0. So we can have scalars that are both positive and negative, but I will typically refer to those as the magnitude. Maybe I'll be a little bit more careful here, and I'll just say a size. So scalars have a size. How big is the scalar? Well, there are other quantities that cannot be described just with the size of the quantity. Those are quantities that have direction along with it. For example, if I want to describe my motion, Well, the first thing we decided in one dimension is I could have a motion to the right, say your right, or a motion to the left. Those would be different. But we basically describe those as positives and negatives. So how is that different than a vector? Well, or how is that not a scalar? Well, I could also move this way, or maybe up, or down, or something like that. So motion, or a displacement, as we described, displacement, as we described earlier, going from one point to another, is a vector quantity. It's a quantity that has direction, a particular direction, and then a magnitude. How much is that motion? If I'm going to say move to the right, I can move to the right a little bit, which would be a vector with a small magnitude. I could move to the right with a larger magnitude. So, and then likewise I could move that way with a small magnitude, or that way. So vectors are quantities with a direction and magnitude. Now, in this case, when I say magnitude, I want to emphasize the magnitude of the vectors is always positive. Now, that doesn't mean that I can't move in a negative direction, but then it's the direction that tells us or gives us the positive-negative sort of concept. I can move to the right 1 meter or to the left 1 meter. Those would both have the same magnitude, but different directions. Okay, so how do we describe these things? How do we describe these vectors? Well, physically, the easiest way to think of a vector or to describe a vector is to physically think of it like an arrow. An arrow is an object with a particular length. You could have arrows with different lengths. Here's a longer arrow, here's a slightly shorter arrow. You can imagine even a very short arrow or arrows as short as you want. And then arrows can point in different directions. I could point this arrow to the right, the arrow could point to the left, up, towards you, any direction I want, any direction in 3 dimensions. My arrow can point. So we'll think of vectors as physically like an arrow. Now, an arrow has some characteristics where they start at a particular point and end at a particular point. So, an initial point, a final point. But what I want to emphasize is that as long as 2 arrows point in the same direction and have the same magnitude, so if we look at these 2, whoa, not those 2, how about these 2? Here we go. Okay, here are 2 arrows that are the same length, so these vectors have the same magnitude. As long as they are pointing in the same direction, in other words, as long as they are parallel, these 2 vectors, it doesn't matter where they are, we will say that they are equal. Equal vectors. Vectors are equal if they have the same magnitude and the same direction. So as long as they're pointing the same direction, they are equal vectors. Okay, so it doesn't matter where they are equal vectors as long as they're pointing in the same direction. Now that does not mean they're pointing to the same spot like this. These might point to the same spot, but they are, if you can see that, but they are not equal because they're not parallel to each other. So they don't point to the same spot, they just point in the same direction. So as long as 2 vectors are pointing in the same direction, they are the same vector. Okay, very good. Now, how can we go about describing these? Well, let's think about the simplest kind of vector that we can talk about, and that is a displacement vector, moving from one point to another. So let's talk about that. Let's imagine that we decide to go for a walk, or maybe our little person here goes for a walk, and they start at some initial point. So here's our initial point, and they walk. Now, they don't actually have to walk straight. They could walk any way they want. Okay, remember, however they walk, they then end up at the final point. So, they start at the initial point, they end up at the final point, but we don't know what happens in between. It doesn't really matter for the displacement. The displacement is then a vector which goes from the initial point In other words, we put the tail of the vector at the initial point. Let's see, which one did I use here? We put the tail of the vector at the initial point and the point of the vector at the final point, and then that vector is what we call our displacement vector. Whenever we want to indicate that a quantity is a vector quantity, we'll put a little arrow sign on top of it. Now, some people might draw the arrow like that, but just for simplicity's sake and for speed, I will typically just put half of that point on it. So this will be our vector sign. And anytime you want to talk about a particular quantity as a vector, the vector quantity, make sure that you put the little arrow on top to indicate that's a vector. If I want to talk about the magnitude of the vector, so just what is the length of this, sometimes we use the symbol absolute value sign. But in this case, when we put it around a vector, it's not an absolute value sign, it's a magnitude sign. So this means the magnitude of the vector. And then typically, if we just write the quantity without the vector sign on top, that just means the magnitude of it. In other words, what's the magnitude of the displacement vector would be the length. What's the length of this vector? How far was the overall motion? Remember, this is not necessarily the distance traveled by the person. So the person could be wandering around all over the place and have a much longer distance than actually the person ended up. But the displacement just describes what's the overall motion from the initial point to the final point. What's the net result of the motion? Okay, there we go. So that's the displacement. Now, how would we go about combining vectors? How do we combine vectors together? Well, the easiest way to do it is to think about combining displacement vectors. We will determine a way of combining displacement vectors which will then work for all kinds of vectors. Any kind of quantity that's a vector quantity, in other words, with direction and magnitude, will add the same way as displacement vectors. So let's take a look at that. Let's imagine that our little person starts out at some initial point. We'll call it P1. And then the person walks to some other point, P2. So however they walk, they end up at some point, over here we'll call it P2. So what is the displacement vector? The vector that goes from P1 to P2. There we go. That's our displacement. We'll call that D1, our first displacement. But then let's imagine our person goes for another part of their walk. Where do they start? Well, they're starting where they ended up the first time. They're starting at P2. So then they walk and they end up at some other point. We'll call it P3. So here's P3, point 3. Well, what is their second displacement? Their second displacement goes from their initial point here to the final point here for the second part of their walk. So the second displacement will look something like that. And we'll call that vector D2. So here we've had our person go from point P1 to point P2, and then afterwards from P2 to point P3. We might like to describe the overall displacement. So what is the final result of both of these displacements, considering the initial position as P1 and then the really final position of P3? Well, what would that displacement look like? Well, that's pretty straightforward. All we have to do is draw a vector from P1 to P3, and that will call our overall final displacement D. And what we will write then is D1 plus D2 is equal to D. This is a vector addition. the addition of vectors. This does not mean that the length of D1 plus the length of D2 equals the length of D. That is absolutely not the case. But this is a different kind of addition, vector addition. And when we're adding vectors, how do we do it? Well, this is going to be our standard model for adding vectors. When we want to add two vectors together, let's say D1 and D2, what do? We take the tail of D2. So the tail, remember, we've got a tip or a head of a vector, and we have a tail or the back end. We'll refer to this as the tail of the vector, and the tip or the head of the vector. We take the tail of the second vector and put it at the head of the first vector, draw it in. The sum, or the resultant of the two vectors added together, is then a vector that goes from the tail of the first vector to the head of the second vector. Okay? So how do we add these? We add them head to tail. And if we actually had a third vector, you could imagine if we took another part of the walk, maybe a vector over here, then the final result would go from here to here, and we would put that third vector head to tail. So how do we add vectors? We put them head to tail, head to tail, head to tail. There we go. Very, very good. This is going to be our model for vector addition. Let's look at one thing first, or the next thing. What if we, rather than taking displacement D1 and then displacement D2, what if we went the other way? What if we took displacement D2 and then D1? Well, starting from the same point, if we took displacement D2, that would mean taking this vector, moving it right down here. Remember, this vector would be the same as this vector as long as it's the same length and the same magnitude, same length, same direction. So I'm just going to draw D2 starting down here, and I'll try and do that as best I can. There we go. So that's pretty good. So that would be the same as D2. But then we added D1. So let's take D1 and move it up here, and what do we get? Here's D1. Well, where does that take us? It takes us to exactly the same point. We notice that D1 plus D2 is the same as D2 plus D1. D1 plus D2 is equal to D2 plus D1. In other words, vector addition is commutative. It doesn't matter what the order of the vectors is that we're adding together. And you could add in another one and another vector and another vector, as many as you want. D1 plus D2 plus D3 plus D4 plus blah, blah, blah is equal to, and then you can put them in any order you want. D3 plus D1 plus D4 plus D2. Any order you want, you will end up with the same result, the same sum. We call this the parallelogram law of vector addition. We know that if we take this side and put it up here, these are not exactly parallel, but close. And this side over here, what does it make? It makes a parallelogram. And we know that the two sides of a parallelogram are parallel. This one is parallel to this one. And we know the lengths of the opposite sides are the same. So same length, same direction. That shows us that we will end up at the same point. Very, very good. We've got a very, very important rule there for addition. I've written it with 2, but remember you can put in as many as you want. Now sometimes it's useful to be able to figure out exactly quantitatively, given some initial displacements, what's the final displacement look like? What's the length? What are the directions? Well, there's a way that we can actually quantitatively describe the direction. Let's take a look at that. Let's take a couple of simple displacements and see if we can figure out how to combine them quantitatively.